Welcome to Study Loop.
This is the answer to Chapter 13, problem number 57 from the Smith Organic Chemistry textbook. And in this problem, we are asked, explain why a ketone carbonyl typically absorbs at a lower wave number than an aldehyde carbonyl. So 1715 versus 1730 wave number. Obviously I've drawn a lot of this already. I tried to upload this previously and it didn't work. So rather than redraw all of this, I've erased a couple parts that I'll draw back in, and I'll talk about what's drawn here. The answer to this question is going to be found by looking at the charge-separated resonance structure for each of these two molecules. So I've drawn a simple ketone and a simple aldehyde here. So just a methyl group for each. In the charge-separated resonance structure for the ketone, there are two methyl groups, one to either side of the carbonyl carbon. And so these carbons are going to act as electron donating groups. And so they're going to donate electron density towards that positive charge in this resonance structure. And so this is going to stabilize this resonance structure. So that's a somewhat stable resonance structure. So looking at the aldehyde, we only have one methyl group that's able to do that. So the hydrogen can't do that. The one methyl group is able to donate electron density towards that positive charge. This is going to be less stable. We're comparing a more stable charge-separated resonance structure to a less stable charge-separated resonance structure. We expect the more stable resonance structure to contribute more to the resonance hybrid. What this means, in effect, is that for the ketone carbonyl has more single bond character than does the aldehyde carbonyl. It's not a lot, right? We're talking about a difference, 1715 versus 1730. That's not a huge difference, but it is somewhat of a difference. And that difference can be attributed to the fact that the ketone carbonyl bond has more single bond character than the aldehyde carbonyl bond does. And again, that's going to be because the charge-separated resonance structure for the ketone, in which the carbon and oxygen do only have a single bond, is more stable than the corresponding resonance structure for the aldehyde. And so the ketone's charge-separated resonance structure is going to contribute more to the resonance hybrid for that molecule than will the corresponding resonance structure for the aldehyde. The ketone carbonyl has more single bond character, so its absorption is a little lower than the aldehydes. And that's the answer to Chapter 13, problem number 57.